When you throw a baseball, the laws of physics allow you to calculate exactly where it will land. This is governed by a classical rule called the principle of least action. It dictates that any moving object will naturally take the specific path that expends the least cumulative energy. Because of this strict rule, our macroscopic universe is entirely deterministic and computable. It allows human beings to confidently engineer reality. We use the exact same math to calculate a 90-mile-an-hour pitch as we do to map the orbital mechanics of a satellite, all without any uncertainty. But shrink that baseball down to an electron, and predictability collapses. In the double-slit experiment, a particle faces two openings. Instead of choosing one, it enters superposition, traveling multiple paths simultaneously to create a wave pattern. To make mathematical sense of this multipath chaos, physicist Richard Feynman developed a method known as the path integral. He realized that to predict the behavior of just one quantum particle, physicists had to calculate an infinite number of theoretical zigzagging trajectories. Feynman's method worked, but the computational load was staggering. It built a firm conceptual wall, cementing the idea that the simple single-path rules of classical mechanics could not map the quantum world. Recently, researchers at MIT decided to test that boundary, looking back to the classical principle of least action to see if it could be adapted. Their core insight was to tweak the classical formula so it could accommodate multiple simultaneous paths. They did this by introducing a single variable, density. Think of density like a high-pressure hose spraying a concrete wall. We don't calculate the exact trajectory of every single microscopic droplet. Instead, the fluid dynamics naturally create a predictable distribution. A high density of water hits the center, meaning there's a high probability of finding droplets there, while a lower density scatters to the edges. By applying this fluid logic to subatomic particles, the MIT team found a way to treat complex quantum probability as a solvable, classical distribution of mass. They applied this fluid logic to the double-slit experiment. Looking at this schematic showing the classical action paths labeled phi1 and phi2 emerging from the slits, instead of calculating infinite zigzagging routes, you only need to calculate a finite set of simple classical paths. On this density plot, we see what happens when you weight those few classical paths with a fluid density distribution. The oscillating green curve perfectly reproduces the particle's quantum probability pattern. This classical density calculation achieved the exact same result as the Schrödinger equation, the foundational formula of quantum mechanics. By replacing infinity with fluid density, the researchers proved that quantum waves can be exactly computed from simple classical action. The foundational math of classical physics, the Hamilton-Jacobi equation, and the quantum Schrödinger equation are structurally identical once that path density variable is slotted between them. This has immediate, practical stakes for the hardware of quantum computing, which relies on qubits to process information. The engineering bottleneck is that qubits operate with nonlinear, chaotic energies. Tracking, modeling, and stabilizing their exact states has always required enormous computational power. Engineers can now use this classical shortcut to bypass those infinite path calculations entirely. It provides a vastly more efficient way to model behavior and scale quantum hardware. The quantum realm isn't driven by incomprehensible magic. It is simply our everyday physical reality playing out in a denser, multi-path form.